Thank you for your presenting and also for our guest. My topic is simulation of fluid flow. Sorry. Simulation of fluid flow in enhanced geothermal system and coupled thermal hydromechanical modeling. In this topic, we have first introduction, problem statement, literature review, methodology, research finding, and finally the conclusion. First, we are going to talk about the heavy oil and conventional oil importance, what we are facing with. And in general, heavy oil is, as we know, an important part of the world's oil and gas resources. So in this area, we combine the heavy oil with geothermal. So here, in this schematic of picture, we can see we have two parts. The first part is the deep geothermal reservoir. The second part is the heavy oil reservoir, which we are combining and processing this two systems together. And we have three production, which is oil, steam, and electricity, which we are mostly focusing on oil production. And in main point, heating the reservoir.
Sorry to disturb you. Can you share the big screen, because right now we can see the screen that have the next slide.
Oh, sorry.
Thank you.
Just a moment, please. Okay. Is it okay right now?
Yes,
Hello.
it's clear. Yes.
Okay. Thank you. Here, first we have. So. Yeah. First problem statements, which we have metaphysics phenomenon are already involved, coupling the phenomenon, numerical simulation and optimization, and the effects of fluids and heat flow modeling, which after combination of both systems. And here we combine, like if we see this cycle for first for hydrological, then thermal, then it turned to mechanical and back from mechanical to hydrological, which means like we are recycling in the same way the water and the heat, which is come out by steam. So this is what we're going to showing this research, and we are just sorry. For methodology, we already combined the mathematical modeling of governing equation, constitutive equation, and Here we can see the whole geological porous media models for the thermal hydromechanical processing in heavy oil reservoir, which is mechanical constitutive model, which we already mentioned before, fluid and steam flow model, analysis of head flow in heavy oil reservoir, and finally the solution method. The same for mechanical constitutive model and fluid and steam flow model, which we already mentioned here. And also analysis of the head flow in heavy oil reservoir, which is come out after the cooling system. We are cooling down the heat in the cooling system, then we're injecting back inside of the reservoir for our ideal steam, like hot water and steam quality. And this is the solution method. We reduce the bandwidth, as I already mentioned. We're going to cool down the steam and bring it back to the reservoir. We jump to research finding. Like here, I want to give more information. Here we have 4 wheels. The first wheel is here, water injection. The water injection is still, it is, we can say like normal water also can be hot water, but when we come to the hot plates in deep geothermal reservoir, after this, when we're injecting this, we are injecting different water and with different pressure, with different temperature to see the behavior of the plate. So here we bring back the steam. After the steam will come, we have it's already heating the turbine and generating electricity for power generation. For bringing back the steam, as we already mentioned, for steam controlling or cooling down the steam, we're going to inject this back inside of the reservoir. This reservoir is, as we already mentioned, is heavy oil reservoir for lowering its viscosity. And also by injecting steam, it will also receive some pressure to flow back inside of reservoir and for oil production, and which we already mentioned here. So for this stage, we have 2 systems, 2 simulation staff, and also modeling for both of them. So here we already said like for numerical simulation optimization, design and sensitive analysis. So how we going to manage this one, which is our optimal outcome? This is numerical model for enhanced geothermal reservoir, which we run it with computer modeling group or CMG. And here we can see the relative permeability curve, which is oil wet. And this for hydraulic fracturing, it's also show here, and also the properties for well distance. We already selected 3 well distance, like 100 first, second 150, and then 200. Then finally, we find out which one is our optimal. And also here, water saturation flow, which we can see here. And here is the heat distribution or temperature distribution. We will find out how it is effective for our plate. This is for well distance 100 meter. And we can see the temperature is normally like distributed inside of the reservoir. This is the outcome, which we can see like we inject first 80 meter cubic over day, then 100, 120, then 140, then 160 for all different distance, and also the temperature should be 70, 75, 80, 85, and 90 degrees. The same way, we can find out, we can find out here how the relative permeability is moving, and also the same way here we can find out which is not so much optimal. So we move to the next one. Here is for well distance 150, which we can see the head distribution is a little like smoother than before. So this, if we inject like higher temperature, of course, this would the reservoir would receive much more heat, but the affection of that will receive for the next graphs, which we can see here. So as long as we can see here, for injecting the rates of like 80 meter cubic over day and to 160 meter cubic over day, so we can find out the injection rate of 120 meter cubic over day is smoother, like it is almost stable, but still not that much. But if we can see like injection rate of 100 meter cubic is also smooth, which is can continue for almost like 10 years, like smoothly, and which is reliable, much better than 160. For 160, the pressure will go very high and it will drop down by years. So here, so we can see also the main point is the temperature. We can see here, if we can compare, this is for the 160 meter cubic over days, actually good one. But in the same time, we can see the temperature with same amount with different temperature, like 90 degree, it will go still not too much different, but still we can see that it will go high, then by years it will decrease. So still we can say, okay, this is also can be optimal, but still not yet. So here we can see the pressure, which is the most important part of our reservoir. We have, in this case, we will find out the pressure rate, like 25 kPa is already a normal one, which show with the same rate injection, water injection with 100, which we can see the temperature should be 80 degrees. So we can find out here the optimal is injection rate of 100 meter cubic with 80 degree Celsius, can keep the reservoir pressure in stable mood. So here we already tried the well distance of 200 meters. We will find out what is the difference here. And here we can see the temperature is going high. In the same time, the injection of, if we just keep in the middle, like 120 meter cubic, it is still very high. It's going like all go up, and the pressure is not stable. Normally it is like start from 0, suddenly it's go high. So it's also not optimal. And this can be optimal, but the permeability is a little bit unstable, not in one stage. It can be like in 2-3 stages, not stable. So we choose, we will go for the result and we find out which one we can choose. And that's for, now we come to a heavy oil reservoir. After injecting the steam, hot water with steam quality, which is over than 100 degrees Celsius. So here is our main point. And the area which we choose it for this simulation is Bohai. Bohai is offshore, which is located in also in China, but the same way there are lots of wells already shut down, and we are using the same wells for using for this simulation. We use 2 wells which were already drilled, but we already suggested 2 other wells for injection of hot water and receiving back the steam. Still, all water related permeability, you can see here, this is the relative permeability of heavy oil reservoir, which is oil wet. And here, gas relative permeability, so we can just move on, and also water and gas saturation model. You can see not too much water, which is usually heavy oil reservoirs condition like that. And here we can find out for sensitive analysis of steam injection of 150 degrees Celsius to 200 and 250 and well distance of 100 meters. So for this model, which is we keep the well distance for 100 meters, and in the same time we are injecting different temperature steam, so we can find out this one steam injection of 150, and we see the distribution of heat is okay, but not covering a bigger area. Here is still the same for 100-meter model with different injection. For steam injection of 200 degrees Celsius, we will see how it's distributed, and still it's okay, but not too much, like not cover a big area of a reservoir. But here we can see if we inject like 250 degrees Celsius, so it can see clearly the reservoir is heated up with a huge amount of temperature. So in this case, we will find out which one is still optimal for our reservoir. But as long as we see here, it looks better than two others, but still we cannot judge if it's optimal or not. But here we can see sensitive analysis of steam injection 150, but here, as we can see, the well bottom hole pressure is very high. So for well distance of 100 meters. Here also, oil rate ratio, and here oil rate ratio with average temperature and oil steam ratio. So we can see the temperature is the oil steam ratio is high in entire field. Here for steam injection well distance, here we selected 150 meters. So with steam injection of 150 degrees. The same, but steam injection for 200 degrees. And still we need to move on for 250. We'll see the distribution of heat is much bigger than two others. But here, bottom hole pressure 150, 200, and 200, 200 and 250 for this one. And you can see it is start suddenly very high, which is a little bit hard to control if we inject this much temperature. And here, the same. For cumulative oil, like for well distance 150, we can see it's all smoothly and increasing from down to up, like until we can say till 2030 or maybe 2040, it still work. For this one, like steam injection of for 200 meter, we just this time selected 200 meter well distance, and we will see what will happen with steam injection of 150, and this is for 200, and finally this is for 250. So we will see the temperature is like cover some some part, but not bigger as 150 meter. But still, we cannot judge which one is optimal until we see the graphs, which is for well bottom hole pressure, which is suddenly go high for different, even for different temperatures. Still, the first move is very high, but it's not smooth from 150, 200, and 250 degrees. And here for oil ratio is also, but as long as we see it can still continue until 2040, but our main optimal years are 2030, since we're going to combine it with geothermal system. And finally, the conclusion is in a computer modeling group, since we are doing mostly prediction plus modeling for this research area, so we find out the result of combining two systems, EGS and EOR. We can hit the heavy oil reservoir, which huge temperature. In the same time, we still have some electricity production, steam production, and also oil production, which the optimal injection, water injection is 150 for the heavy oil reservoir. And the same way, after optimizing the same model with the previously specified factors such as well distance, different steam injection, temperature injection, and placement on horizontal well production, a sufficient modification was considered for a purpose of achieving a steady outcome in both steam and oil production. Thank you so much for your attention.